Hey everyone, this is Dr. Walker. In this video, I'm going to go over the example from video 208 on electric field. And this example is going to show us how the electric field can affect the motion of an electron when that electron is placed within that electric field. Let's take a look. This problem says an electron is released from rest in a region where there is a uniform electric field of 5900 newtons per coulomb. What is the speed of the electron after it has moved a distance of 1 centimeter? So we can see that the electron was starting from rest, but because it is in that field, then the speed is going to change because we're looking for the final speed. So the first thing I'd like you to do is write down all of the givens that you can think of. Anything that is going to be relevant to this problem. And in order to think of all the givens, you might also need to think about which equations that you're going to need to use, because that's going to make you realize that you need to write down a few extra givens. So pause the video and think about it. And let's go ahead and take a look. So let's just write down the most obvious givens first that are explicitly given, such as it's released from rest, and linking that to looking for the final speed. Then whenever something starts from rest, we say the initial velocity is 0. And then in a region where there's a uniform field of 5900, so that one is explicitly given there. Electric field is 5900 newtons per coulomb. What's the speed of the electron? So we're looking for the final speed. We can call it VF. After it has moved a distance of 1 centimeter. So we can call it d, or we can call it delta x, because this electron is just going to move in a straight line. And so we can call it delta x, it doesn't matter. It's going to be 1 centimeter. And we always like to write things in standard units, so for distance it's meters. Let's convert the 1 centimeter to meter. And we're going to divide by 100 to do that. So it's going to be 0.01 meters. So that might be all that you see, upon a first look. And that's all I would see too. But we need to think about, well, how are we going to solve this problem? So we have to really understand what is happening in this problem. So what's happening in this problem is that there's an electric field, and the electron is within this field. Let's say that the electric field is this way. All right, it's a uniform electric field. So because this electron is within this field, it's going to experience a force. That's what we learned in the previous video. So the force is going to be important. We're gonna need to find that force. What's the relevant equation that relates the force that it experiences to the electric field? You remember this equation, E equals F over Q. We learned that equation as well. So the electric field is related to the force that the charge experiences when it is placed within that field. So now this gives us another given that we need to write, the charge. The charge is the electron. So Q is the charge of an electron. And we can actually just deal with magnitudes here, just amounts of electric field. We can take the absolute value of the charge so that if we know the electric field, we can find the force, just the amount of it, not worrying about the direction. So the charge itself is negative 1.6 times 10 to the negative 19 coulombs. That's the charge of an electron. But we can just find the absolute value of that and just use 1.6 times 10 to the negative 19 coulombs for the charge. Okay, so keep thinking. Once you know the force, then how is that going to help you find the final speed? Well, what you should realize is that you are given V initial, V final, and distance or displacement. Those sound very much like the kinematic quantities from Physics 1. And remember that if you knew 3 quantities, you could find a fourth one, and the 5 quantities that we have for kinematic quantities were the initial speed, final speed or velocity, delta x, the displacement, the time, and the acceleration. Those were the kinematic quantities that we learned about. If we know 3 of them, which we do here, then we can find one of the unknown, which could be t or a. So looking at this, which one do you think is going to be relevant to this problem? To find VF, do you think time or acceleration is going to be relevant? Well, got to think a little bit here, but if we know force, then we know that force is also related to acceleration. We know from Newton's second law that acceleration is force divided by mass. So this ends up being a 3-step problem. We're going to need to find the force using this equation, E equals F over Q. We're then going to need to find the acceleration using force per mass. And then once we have the acceleration, then we can find our unknown here. And I may have said that we were given VF, but VF is actually our unknown. Sorry about that. A is now going to be a given, and that will allow us to find VF using a kinematic equation. So step 1, step 2, and then step 3 is we're going to find VF. Can you go through your kinematic equations and write down the one that we're going to be using? The one that has V initial, V final, delta x, and acceleration? It's going to be V final squared equals V initial squared plus 2a delta x. So this is a pretty difficult problem because you have to really think and visualize what is happening here. You can't just find random equations to plug things in. They have to be relevant to the problem. So now we are ready to plug and chug. So the first step is to find that force. So rearranging this equation, E is F over Q, then we get the force is the electric field times the charge. So we're going to multiply 5,900 times 1.6 times 10 to the negative 19 coulombs. That's going to give us 9.44 times 10 to the negative 16 newtons. So that's the first thing, is this electron is going to experience a force. We're actually going to learn in the next section that the force is actually going to be to the left, but it really doesn't matter here because everything is moving in a straight line. So we can just use the magnitude of the force, right, the distance that we were given, and everything will work out. So let's look at the second part here. We're looking for the acceleration. Acceleration is force divided by mass. So we need the mass of the electron. So that should be another given that we write down. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. That's from your chart. So a lot of times you're going to need to write that down, even though it might not be clear that you might need it right away until later in the problem. So we're going to use the force that we just found, 9.44 times 10 to the negative 16 newtons divided by 9.11 times 10 to the negative 31 kilograms. And that's going to give us an acceleration of 1.04 times 10 to the 15 meters per second squared. So what I was saying about directions, right now it doesn't matter if the acceleration is to the left or to the right. If the acceleration is to the right, then the electron will move to the right. If the acceleration is to the left, the electron will move to the left. It doesn't matter because the problem gives us the distance moved, so it's not specifying which direction. And the question is asking us for the speed, which does not involve a direction. So the velocity, the final velocity, could be to the left or to the right. but the speed is going to be a positive number, so we're not asked about the direction. So let's go ahead and do that final step. I'm going to do it in the corner here under number 3. So let's go ahead and solve for v final. And because the electron starts from rest, let's go ahead and cross out that term that is equal to 0. And then to solve for v final, we're going to take the square root of both sides. So v final equals square root of 2a delta x. And then we're going to plug in the values that we have. So v final is equal to the square root of 2 times 1.04 times 10 to the 15 times delta x, which was 0.01. So plug all of that in the square root, and we're going to get 4.55 times 10 to the 6 meters per second. So that is our final speed. Now, just in case you are curious about this whole direction thing, we're going to see in the next video that the force experienced by the electron is actually to the left, because an electron always experiences a force in the opposite direction as the electric field. The force is actually going to be to the left. And if we hadn't used the absolute value of the charge in this equation, then we would have gotten a negative number for the force, telling us that the force is indeed in the opposite direction as the electric field. And then as far as using the kinematic equations, first of all, we would have gotten a negative acceleration because the acceleration and the force are always in the same direction. So we would have gotten a negative acceleration to plug in here to find v final. However, since the electron would also be traveling to the left, the actual displacement of the electron, the delta x, would actually have been negative 0.01 meters if we were paying attention to direction. And in that case, both negatives would have canceled out. So for this problem, the directions didn't really matter. We would get the same answer either way, whether or not we paid attention to the direction. So I just wanted to let you know about that in case you were wondering. In general, direction is going to be very important, but it will be very explicit in the problem that direction matters, and you're going to be given an indication of which way things are going to begin with. So I hope that this video was helpful. It was a difficult problem, but it was a really good review problem of a couple of items from Physics 1, and also how to use the equation for electric field that relates the electric field and to the force that the charge is experiencing when it's within that field. So I will see you in the next video.